determine the appropriate transformer size, we need to consider the load. The load is 200 amps of single phase. This equates to 115.5 kVA calculated as 200 amps times 277 volts times 0.866. To account for fluctuations and future expansion, it's wise to incorporate a safety factor. Let's assume a 20% safety factor. Multiply the calculated kVA by 1.2 to get 138.6 kVA. Based on this calculation, a 150 kVA transformer would be a suitable choice. The 480 volts delta to 208/120 volts transformer mentioned would be appropriate. Connect the primary side to the 480 volts delta service. Connect the secondary side to the 208/120 volts panel. Install a 3-phase 4-wire panel rated for 208/120 volts. Use wiring appropriate for the amperage and voltage requirements of the loads being served. Several safety considerations are vital. Firstly, obtain the necessary permits. Contact the local building department to obtain permits for the work to ensure compliance with local regulations. Secondly, use qualified materials and equipment. Purchase certified equipment from reputable manufacturers to ensure quality and safety. Thirdly, follow all electrical codes. Ensure that the installation meets the National Electrical Code, also known as NEC, and any local regulations. Fourthly, have the work inspected by a licensed electrician. Once the installation is complete, a qualified electrician can inspect the installation for safety and compliance. It is highly recommended to engage a licensed electrician to perform this work, especially if there is a lack of qualifications to do so. Working with high voltage electricity can be dangerous and should only be undertaken by trained professionals. Firstly, the transformer primary voltage rating must match the supply voltage. Select a transformer with a primary voltage rating that matches the incoming 480 volts delta supply. Secondly, the transformer secondary voltage rating must match the load voltage. Select a transformer with a secondary voltage rating of 208/120 volts to supply the panel. Thirdly, calculate the total apparent power. Estimate the total apparent power, measured in kVA, that the house will draw. Account for all the loads, including lighting, appliances, and any other electrical equipment. Fourthly, apply a safety factor. Multiply the total apparent power by a safety factor, typically 1.2 to 1.25, to account for future expansion and unforeseen loads. Fifthly, select a transformer with a kVA rating. Select a transformer with a kVA rating equal to or greater than the apparent power plus the safety factor. This ensures that the transformer can handle the load without overheating. Sixthly, consider the transformer type. Choose between a dry type or liquid-filled transformer, depending on the application and environment. Dry-type transformers are typically used indoors, while liquid-filled transformers are used outdoors or in areas with high humidity. Seventhly, check the transformer efficiency. Select a transformer with a high efficiency rating to minimize energy losses and reduce operating costs. Eighthly, verify the transformer impedance. Ensure that the transformer impedance is compatible with the system impedance to avoid voltage drops and other issues. Ninthly, install overcurrent protection. Install overcurrent protection devices, such as fuses or circuit breakers, on both the primary and secondary sides of the transformer to protect against overloads and short circuits. Tenthly, ground the transformer properly. Ground the transformer according to the National Electrical Code and local regulations to prevent electrical shock hazards. Firstly, calculating single-phase load from amps. The formula is kVA equals amps times volts divided by 1000. For a 200 amp single-phase load at 277 volts, is 200 amps times 277 volts divided by 1000, which equals 55.4 kVA per phase. Secondly, calculating three-phase load. The formula is kVA equals volts times amps times square root of 3 divided by 1000. This formula accounts for the three phases and the phase difference. Thirdly, the total kVA calculation. Since you have two phases, multiply the single phase kVA by 2. So 55.4 kVA times 2 equals 110.8 kVA. This is the total kVA needed to supply the 200 amps load across the two phases. Fourthly, applying a safety factor, increase the total kVA by a safety factor, typically 20%, to account for future loads and voltage fluctuations. Multiply 110.8 kVA by 1.2, which equals 132.96 kVA. Fifthly, selecting the transformer size, choose a transformer with a kVA rating equal to or greater than the calculated value with the safety factor. A standard transformer size that would meet this requirement is a 150 kVA transformer. Firstly, understanding the 480 volts delta configuration. In a 480 volts delta system, the voltage between any two phases, also known as line-to-line voltage, is 480 volts. There is no neutral connection in a standard delta configuration. Secondly, understanding the 208/120 volts Y configuration. In a 208/120 volts Y system, the voltage between any two phases is 208 volts. The voltage between any phase and neutral, also known as line-to-neutral voltage, is 120 volts. Thirdly, the transformer primary connections involve connecting the three primary windings of the transformer to the three phases of the 480 volts delta system. Each winding should be connected between two phases. Fourthly, the transformer secondary connections involve connecting the three secondary windings of the transformer in a Y configuration. The common point of the Y is connected to the neutral conductor. The three-phase conductors and the neutral conductor are then connected to the 208/120 volts panel. Fifthly, the grounding requirements. Proper grounding is essential for safety. The neutral point of the Y-connected secondary should be grounded according to the National Electrical Code and local regulations. This ensures that any fault current will flow back to the source, tripping the overcurrent protection devices. Sixthly, the overcurrent protection involves installing circuit breakers or fuses on both the primary and secondary sides of the transformer. These devices protect the transformer and the connected loads from overloads and short circuits. Firstly, calculate the total load in kVA. Determine the total kVA required to supply the house. This should include all electrical loads such as lighting, appliances, heating, ventilation, and air conditioning, and other equipment. Secondly, apply a demand factor. Apply a demand factor to the total kVA to account for the fact that not all loads will be operating at the same time. The demand factor is a percentage that represents the maximum amount of power that is likely to be used at any one time. The demand factor can be found in the National Electrical Code, also known as NEC, or from local utility companies. Thirdly, calculate the transformer kVA rating. Divide the total kVA by the demand factor to determine the required transformer kVA rating. This will ensure that the transformer is large enough to supply a house's electrical needs. Fourthly, consider future expansion. Consider future expansion when selecting the transformer kVA rating. It is always better to select a transformer that is slightly larger than needed to accommodate future electrical loads. Fifthly, select the transformer voltage rating. Select a transformer with a voltage rating that matches the voltage of the incoming power supply and the voltage required by the house's electrical system. The most common voltage ratings for residential transformers are 480 volts delta primary to 208/120 volts Y secondary. Sixthly, select the transformer type. Select a transformer type that is appropriate for the location and environment. Dry-type transformers are typically used indoors, while liquid-filled transformers are used outdoors. Seventhly, install overcurrent protection. Install overcurrent protection devices, such as fuses or circuit breakers, on both the primary and secondary sides of the transformer to protect against overloads and short circuits. Eighthly, ground the transformer. Ground the transformer according to the National Electrical Code and local regulations to protect against electrical shock. Ninthly, hire a qualified electrician. Hire a qualified electrician to install the transformer. The electrician will ensure that the transformer is installed correctly and safely. 10thly, obtain necessary permits. Obtain the necessary permits from the local building department before installing the transformer. The permits will ensure that the installation meets all applicable codes and regulations. The first step involves identifying all electrical loads. Make a list of all the electrical loads in the house, including lighting, appliances, heating, ventilation, and air conditioning, also known as HVAC, and other equipment. For each load, determine the power consumption in watts or volt amps. Secondly, calculate the total connected load. Add up the power consumption of all the loads to determine the total connected load. This is the total amount of power that would be used if all the loads were operating at the same time. Thirdly, apply demand factors. Apply demand factors to the connected loads to account for the fact that not all loads will be operating at the same time. Demand factors are typically expressed as a percentage of the connected load. The National Electrical Code, also known as NEC, provides demand factors for various types of loads. Fourthly, calculate the maximum demand. Multiply each connected load by its corresponding demand factor. Then, add up the results to determine the maximum demand. This is the maximum amount of power that is likely to be used at any one time. Fifthly, determine the transformer size. Select a transformer with a kVA rating that is equal to or greater than the maximum demand. It is always a good idea to select a transformer that is slightly larger than needed to allow for future expansion. Sixthly, consider voltage drop. Ensure that the transformer is sized properly to minimize voltage drop. Voltage drop is the decrease in voltage that occurs as electricity flows through the wiring. Excessive voltage drop can cause appliances to operate inefficiently and can even damage them. Seventhly, comply with codes and regulations. Ensure that the transformer installation complies with all applicable codes and regulations. The National Electrical Code, also known as NEC, provides detailed requirements for transformer installations. Eighthly, use qualified personnel. Hire a qualified electrician to install the transformer. A qualified electrician will have the knowledge and experience to install the transformer safely and correctly. Firstly, determine the total load. Calculate the total amount of power that the house will require. This can be done by adding up the wattage of all the appliances, lights, and other electrical devices that will be used in the house. Secondly, apply a demand factor. A demand factor is a percentage that is used to account for the fact that not all electrical devices will be used at the same time. The demand factor will vary depending on the size and type of house. Thirdly, calculate the transformer size. The transformer size is calculated by multiplying the total load by the demand factor. For example, if the total load is 100 kVA and the demand factor is 80%, then the transformer size would be 80 kVA. Fourthly, select a standard transformer size. Transformers are typically available in standard sizes, such as 25 kVA, 50 kVA, 75 kVA, 100 kVA, and 150 kVA. Select a standard transformer size that is equal to or greater than the calculated transformer size. Fifthly, consider future needs. When selecting a transformer size, it is important to consider future needs. If there is a plan to add more electrical devices to the house in the future, then it is important to select a transformer that is large enough to handle the additional load. Sixthly, consult with an electrician. It is always a good idea to consult with an electrician when selecting a transformer size. An electrician can help to determine the total load, apply the appropriate demand factor, and select a transformer that is the right size for the house. Firstly, calculate the total load. To accurately size the transformer, begin by determining the total electrical load of the house. This involves listing all electrical appliances, lighting fixtures, and other devices, and noting their respective power consumption in watts or volt amps. Secondly, determine demand factors. Not all electrical loads operate simultaneously. Demand factors account for this by estimating the percentage of total connected load that is likely to be in use at any given time. Consult the National Electrical Code, also known as NEC, for appropriate demand factors based on the type and size of the residence. Thirdly, calculate the maximum demand. Multiply each individual load by its corresponding demand factor. Then, sum up these adjusted loads to determine the maximum demand, representing the realistic peak power requirement of the house. Fourthly, incorporate a safety margin. Add a safety margin of 20% to 25% to the maximum demand to accommodate unforeseen future load growth or fluctuations. This buffer ensures the transformer is adequately sized for both current and potential electrical needs. Fifthly, calculate the required transformer kVA. Convert the maximum demand plus safety margin from watts to kVA by dividing by 1000. This yields the minimum kVA rating the transformer should possess. Sixthly, select the appropriate transformer size. Choose a commercially available transformer with a kVA rating equal to or slightly higher than the calculated value. Standard transformer sizes typically range from 25 kVA to several hundred kVA, so select the nearest standard size that meets or exceeds the calculated requirement. Seventhly, consider voltage regulation. Voltage regulation refers to the transformer's ability to maintain a stable output voltage under varying load conditions. Select a transformer with good voltage regulation characteristics to ensure consistent power delivery to household appliances and equipment. Eighthly, evaluate transformer efficiency. Opt for a high-efficiency transformer to minimize energy losses during operation. Higher efficiency translates to lower electricity bills and reduced environmental impact. Ninthly, factor in environmental conditions. Take into account the environmental conditions in which the transformer will operate. Dry-type transformers are suitable for indoor installations, while liquid-filled transformers are designed for outdoor use and can withstand harsh weather conditions. Tenthly, consult with a qualified electrician. It is crucial to consult with a qualified electrician throughout the transformer sizing and installation process. A professional electrician can accurately assess the electrical needs of the house, recommend the appropriate transformer size and type, and ensure safe and compliant installation. To summarize the procedure, the first step involves itemizing all electrical loads within the household, documenting their respective power consumption in watts. The second step entails applying appropriate demand factors to each load, accounting for the likelihood of simultaneous operation as specified in the National Electrical Code, also known as NEC. The third step requires calculating the maximum demand by summing the adjusted loads representing the peak power requirement of the residence. The fourth step suggests incorporating a safety margin, typically ranging from 20% to 25%, to accommodate potential future load growth or fluctuations, ensuring adequate transformer capacity. The fifth step involves determining the required transformer kVA rating by dividing the maximum demand plus safety margin by 1000, yielding the minimum kVA rating the transformer should possess. The sixth step advises selecting a commercially available transformer with a kVA rating equal to or slightly higher than the calculated value, considering standard transformer sizes available in the market. The seventh step emphasizes considering voltage regulation, ensuring the transformer maintains a stable output voltage under varying load conditions for consistent power delivery. The eighth step highlights evaluating transformer efficiency, opting for a high-efficiency model to minimize energy losses and reduce operational costs over time. The ninth step underscores factoring in environmental conditions, selecting a transformer type, dry type or liquid-filled, suitable for the installation environment, indoor or outdoor. Finally, the 10th step strongly recommends consulting with a qualified electrician throughout the entire process, leveraging their expertise to accurately assess electrical needs, recommend the appropriate transformer size and type, and ensure safe and compliant installation practices.